Okay, everybody. So we are talking about systems. Systems is the second part of our linear unit, and we're going to start talking about it in class tomorrow. But first, we need to kind of get an idea of what a system is. And to really understand what the system is, we need to know how to solve it. So, one of the things that you'll be able to utilize when solving systems or finding the solution to systems is graphs. Graphs, we can get a lot of information out of graphs, but in regards to this conversation that we're having now, we can find the solution for systems from graphs. So what the heck is a system? What am I even talking about? A system of equations exists when two equations share the same variables. And we'll mostly be talking about two linear equations, but we're also going to talk a little bit about quadratic linear systems and quadratic systems. So there might be some squared variables in here, but for the most part, we're just going to talk about two regular old lines. We won't have any exponents happening, but they do share the same variables. So there's more than one variable in each of the equations, but each equation has the same letters. So the solution to a system of equations, when we are looking at a graph, it's great because we don't really have to do any math. We just have to look. The solution to a system of equations is the point on the graph, okay? The point on the graph where the two lines intersect. When we talked about quadratic equations, the solution to the quadratic was where the parabola crossed the x-axis. Well, the solution to a system has nothing to do with the axes, but instead has everything to do with where those two lines cross each other. And since it's a point on the graph, we'll write that solution in the form of an ordered pair. Okay. X and Y. There's two exceptions to this rule. If the system is two parallel lines have the same slope. They're always going to be running in the same direction next to each other. And just like train tracks, which is a great example of parallel lines, those two lines will never intersect. They're never going to cross over. The train wouldn't be able to go. So they will never intersect. And no intersection means no what? Solution. If they don't cross each other, then there's no solution. Two lines with the same slope and the same y-intercept are considered twin lines. So if those lines are running, they are identical and they exist on top of each other in one continuous intersection. So if parallel lines meant no solution, twin lines or the same lines means infinite solutions. You could put any number in for the variables in those systems and it would make the system true. Okay, so understanding that the solution to a system of equations is the point where the two lines intersect, what would the solution of this system be? It's going to be this point right here where the two lines cross. So we would write it as an ordered pair, 2, -2. We went over 2 and down 2. So our solution is 2, -2. Pretty straightforward. Okay, but there might be times when you're not given a picture of a graph and instead you're given the system and asked to figure out the solution graphically. So figure out using a graph what the point of intersection is. There's also going to be times when you're asked to solve algebraically, and we're going to talk about those methods in class over the next few days. But in terms of graphing, this could not be any easier. We're just going to pop these two equations into the graphing calculator and check out what the graph tells us. So let's try one. Into my first line, I'll type the first equation that's in the example. So x minus 2y equals 4. There's my first line. Cool. The great thing about Desmos is that I don't even have to get these equations into y equals format, into slope-intercept format. I can just type it in. The second one is y equals x minus 2. Okay, so here we go. We've got the top line is our green line. The bottom line is our purple line. Here's green. Here's purple. Here's the point of intersection. And Desmos is telling me that that point is 0, negative 2. 0, negative 2. Let's try the other one. Clear these out. Okay, into my first line, I'm going to type the first equation in the system. And you'll know systems because they'll be indicated with that little curly bracket on one side connecting the two. So you know it's a system. X plus 3y equals 18. Okay. Ooh, all right. And negative x plus 2y equals 7. Can we move this? Yes, we can. Awesome. All right, so the top line is my black line, the bottom line is my red line, and they meet here at this point, 3, 5. So 3, 5 is the solution to that system. Not too bad. You guys can handle that. Excuse me. All right, what if it gets harder? Does it get harder? I don't know. Graphing a linear quadratic system of equations. So the two examples that I showed you first, let me flip back real quick. These two examples are linear systems. There's no exponents here. There's no exponents here. So they share the same variables. There's x's and y's in both. There's not some random z in one of them. But they have no exponents. So they're just two linear equations. Now we're talking about a linear quadratic system, meaning you've got one linear equation and you've got one quadratic equation. I've got an x squared, there's my quadratic. I've got no variables, there's my linear. All right? So a linear quadratic system is just what it sounds like. It's a system with one linear equation and one quadratic equation where they share the same variables. And there's going to be a difference here. The solutions are going to be different. They're going to be in the same format. They're still going to be in the format of ordered pairs. But there's the maximum of 2 possible solutions to a quadratic linear system. And why do you think that is? Why could we have 2 solutions where before we could only have 1? Well, it's because the graph of the quadratic makes that U shape, and you could have that line going through that U shape at 2 different places. So that's when you have that 2 solutions to the system. But remember, that's the maximum number. It's not going to be 2 solutions every time. You might have one solution where the line just glances off the parabola, and you may have no solutions where they don't intersect each other at all. So why is this? It's the shape of the quadratic or the parabola. Okay, so let's look at these 2 examples in the graphing calculator. Let me go back to Desmos here. Okay, let's clear these out from the linear. And now I've got x squared plus 2x plus 1. X squared plus 2x plus 1. All right. And my next line, negative x plus y equals 3. Okay, get out of here. So you can see, here's one point of intersection. My parabola is the blue line. That's my quadratic equation. My green line is the linear equation. It's that straight line, and it has 2 points of intersection. So the first one here is negative 2, 1. Remember, we can just hover over on Desmos, hover over the point, and it'll tell us. And my second one is 1, 4. Pretty straightforward. Let's look at another example. Okay, my next one is going to be x squared minus 4x plus 3. Let me get my little keyboard back here. X squared minus 4x plus 3. And my line is going to be y equals x minus 1. Get my keyboard out of the way. All right, so my quadratic, my parabola, is this light purple color. And then my line is this black. I've got 1 point of intersection at 1, 0, and 1 point of intersection at 4, 3. Now, if you only have 1 point, then you only have to write the 1 point. And if you have no solutions, then you just write no solutions. Pretty simple. Okay, there's one last piece of this graphs bit here, and that is graphing inequalities. Now, I don't spend a ton of time on this because sometimes it winds up on the SOL and sometimes it doesn't, but it's good to talk about it just in case. The solution of a linear system is the 1 point where the lines cross each other. And the solution to a linear quadratic system is the potential 2 points where the parabola and the line intersect. But those are intersections, right? What about systems of inequalities? Well, with inequalities, it's all about the shading, because when you graph an inequality, just like when you graph an inequality on a number line, you're dealing with shading of that graph. So let's say we have this system. Y is less than or equal to x minus 2, and y is greater than negative 3 plus x. So this first picture shows you the graph of y is less than or equal to x minus 2. This is the line for x minus 2. And since y is less than or equal to, the solutions that are less than the value of the line are shaded in. If it was greater than, the top part of this graph would be shaded. But since it's less than, the bottom half is shaded. And since it's less than or equal to, just like the closed circle on the number line, we now have a solid line for the graph. Okay? And that means that any of the values within this shaded region will satisfy this equation, or inequality, excuse me. Okay, now the second part, y is greater than negative 3x plus 5, that's this second portion here. This is the line for negative 3x plus 5. It's a dotted line because it's only greater than, just like the open circle on the number line. It's a dotted line indicating that there's no equal to portion. And since y is greater than, then it's all the values above that line that are shaded in. If it was less than, then it would be the values below it. But since it's greater than, it's all of these values above. And that just means that any of the values within this shaded region would satisfy y is greater than negative 3x plus 5. So the solution to that system is this section here, which you can see very dark down here, where the shading of both of those inequalities overlaps, kind of like a Venn diagram, where the shading overlaps. So if you're shading both of them, the darkest area, that means that anything within any point, any value of x and y within this area will satisfy both of the inequalities in that system. Okay, so if you were asked for a solution on the multiple choice test, like, the SOL, it could say, is this point, and they could give you a point, a solution for this system of inequalities? And as long as it fell within the darkest shaded area, you could say, yes, it is. Or you could pick a point that falls within that area. So however the question is framed, you're just looking for a point that is within that area of double shading or of overlapping shading. And that is the solution to a system of inequalities. So that's it, guys. That's graphs. And that's how to use graphs to solve systems. Linear, linear-quadratic, and inequalities. And we're going to get into the algebraic methods for solving systems in class. So get excited. But if you have any questions about this, we're going to talk about it briefly in class tomorrow. And other than that, we'll move right on to the actual math part. If you have any questions, let me know. Otherwise, we'll see you soon. Great job.